Thanks, Keith. All right, so as Keith said, I'm Deana Brown, and I'm a PhD student candidate in human-centered computing. So a lot of the work I do focuses on how to apply technologies to address socioeconomic challenges faced by marginalized groups, underserved groups, and I do a lot of that focusing on the immigrant and refugee community. So today I'll be talking about one project in particular, since we have a short time. And this looks at mediating communication in refugee support networks to overcome language barriers. And this is sort of a project that's part of a bigger project to look overall at mediating communication in various family support groups for families that are undergoing long-term sensitive life changes, such as being a refugee or being separated due to immigration status or so on. So every year, up to 70,000 refugees arrive in the US. That's sort of the cap that the US has on the number of refugees that it accepts for a resettlement each year. So basically, Atlanta is 7th in the nation for receiving refugees for resettlement. So Clarkston has a lot of large refugee community. And a refugee is a person who is usually fleeing their home country involuntarily, usually due to fear of persecution, political violence, or discrimination, or other reasons. So if you can imagine you're this family, maybe you're the head of household of this family, you arrived in the US with a wife, a few kids, maybe an older family member, and what you're faced with is 90 days where you're expected to rebuild your life. So if you've moved to the US due to immigration, you understand that that's not a long time. And you're expected to achieve self-sufficiency in this time frame because your federal support, financial support will run out exactly at 90 days. So this support is useful for helping them to pay for rent and so on. At the end of that, they're on their own. So in order to really achieve self-sufficiency, you'll need to interact with well over 24 individuals in this time frame on arrival. So you're looking at caseworkers that you'll need to communicate with, you'll need to be able to get the necessary shots and so on to be able to apply for a residence card, so you'll need to do a lot of doctor's appointments. You have to get your kids enrolled in school if they're a certain age. You'll need to apply for a driver's license or a social security card, so you'll be visiting a lot of agencies. You have to interview for jobs because you need a job. At least one person in the household needs to have a job to be able to support the family afterwards, and a number of other individuals. So we focus specifically this research on communicating with mentors. So a lot of these new refugees are paired with American family who serves as a mentor, and they kind of help them with the social integration aspect and accomplishing tasks during this time frame to help them get on their feet. So things that we may take for granted, like knowing how to take the MARTA, that might not be something that they did before. Well, of course they didn't take the MARTA before, but they might not even understand a subway system or something like that. So the families help with these different tasks, getting a library card, just different things that they need to do. So what we wanted to do is focus on how we can actually improve the mentor-refugee relationship in ways that will improve the outcome in that 90 days of resettlement. So in my discussion with a lot of these mentors and volunteer workers, which I'll get more into, one of the obvious barriers is language. And a lot of new refugees come in not knowing any English. And along with that, they're faced with literacy challenges, so they may not even know how to read or write in their own language. And beyond that, a number of the languages that some of them speak may not be well known. So it might be, for instance, I work a lot with the Burmese family, whereas Burmese is somewhat, a larger language. There are more local languages that a lot of them speak, like Chin Falan and so on, that it might be even harder to get professional interpreters for them. And added to that, there are dialects that they may speak or just variations. So these barriers really limit the livelihood capabilities, limit the tasks, which limit the capabilities of these refugees. So we wanted to understand how technology might play a role in sort of mediating some of these communication challenges that new refugees face on arrival, in ways that allow them to get the most of the encounters they have with the people in their support network in order to improve their livelihood capabilities. So, and essentially a livelihood consists of just the capabilities to be able to create assets or increase your assets, whether physical or social capital, things like that. Increase your material and social resources, and just the activities required to do that to achieve a means of living. So we take a qualitative approach. So we do a lot of, did an exploratory study to try to understand the barriers and opportunities, which I'll get into a bit more. And following this, we created an initial system as a probe which we then deployed to understand the impact it could have on improving these relationships. So for the first part of the study, looking at the barriers and opportunities, this consisted of participant observation. So I spent 6 months volunteering at one of the largest refugee agencies in Atlanta, seeing firsthand what the challenges were for the families coming in. I worked more with the teens, but I had to interact with the parents, which was a challenge, not being able to tell them exactly, your child needs help in this area or so on due to the language barriers. I also did in-home shadowing with these mentor-mentee pairs. So the American families that are paired with the refugee families, they visit they're supposed to visit at least once a week. So I would shadow and observe how they interact, whether using hand gestures and so on, what the challenges were, and I got a bit more insight into what the families had to go through during their transition. And so in addition to speaking with the mentors and the refugees themselves, I also spoke with the professional interpreters that the agencies hire, understanding the limitations of them being able to serve or do their role, and the coordinators as well. So as I mentioned, these refugees need to interact with a lot of people, and in particular with the mentors, the obvious barriers, language, literacy, but they're also incredibly busy, so hard to get in touch with. And then accessibility is also an issue. A lot of them may not use prior technologies like the internet and so on. They do get a phone on arrival, which they call the Obama phone, and they may change the number a couple times, so it's quite tricky to just keep in touch with them. So shifting a bit, after doing the exploratory study, through iterative design with the agencies, developed this version of a system called Rivrtran that's essentially a message exchange platform that does provide support the translation of messages using human interpreters. So the next slide shows sort of what the system is. So it's both IVR platform, which was important, so interactive voice response, a very basic, simple technology. If you call your bank and it says, press 1 to do this, press 2 to do that. We had to implement that due to the literacy challenges for some of the refugees and the fact that they just have a basic phone. So they can access it that way. And then there's also a web client that does have more features that more so the mentors and the translators will use. So as we mentioned, there's this role that the agency sort of created, given our system, where they had volunteer interpreters who were past refugees or so on, so that were doing the translations. And which is important because none of the interpreters actually reside here in Atlanta. So we're able to actually source more interpreters because we didn't need them to be physically present to do that. So for the deployment, this is currently we're still doing the tool is deployed currently. We're 2 months in, so it's meant to be a 3-month deployment. And so far we've done pre and mid interviews, and we've assessed some of the tasks that they've been to date able to accomplish through the system, and also looked at what they were or were not able to accomplish prior to the system. So I'll talk more about that, the data that we have to date. So we have 9 families signed up using the system with their mentors, and they're all Burmese families because it would be tricky to take on a wide range of different cultures at once. So we limited it to that. So we so far analyzed like the messages coming in the platform, and along with the interviews, transcripts. So we noticed that there are these categories of topics so far that people have used the system for. So health, a number of the women come, they're pregnant, so the doctors actually need to interact a lot with them. So the mentors use it a lot to convey more complicated things that the doctor says that they can't use hand gestures to convey, or a 7-year-old to convey. They've discussed, it's tax season, so they've talked a lot about tax fraud. A lot of refugees fall prey to that, where other people, will do your taxes and then it's not done appropriately. So some of the mentors have used it to explain why they should, caution, or just simple things like explaining that we're going to take you to the zoo, and this is what the zoo is, and this is what we'll do at the zoo. These are some of the messages that they exchanged. So in terms of actions, our activities, the system has been used largely for like making schedules. So it was interesting that just telling someone that I'm going to show up at 3 was a difficult message to understand for a new refugee. I mean, if you don't speak English, you just don't speak English. So it used a lot for scheduling, explaining concepts, making requests, and then just being able to send daily greetings, which is not something you would call like a language line to say, hey, what's up, how are you? So speaking of which, so this is sort of what some of the solutions to date were, I guess, prior to the system, in terms of your options for communicating with someone who doesn't speak your language. So there's a language helpline, which sits in a more formal synchronous space, very expensive, about $4 to $7 a minute to use it. A lot of the schools and the doctors will try to use it. They don't always, due to the expense. Another popular one was just the bilingual friend, that is a more informal means of getting translation done, whether real time or not. So we found that Rivrtran sort of sat in this informal asynchronous space, and the informality really allowed it to provide support for lesser known languages or broken version of languages. So broken Burmese, interpreters say, they would speak that because it improved the comprehension of the message than using a formal version of Burmese, or using a more informal dialect that they assess that the person would understand more. They sort of called Rivrtran the anonymous friend. So it was interesting because the style for the interpreters, instead of directly like word for word translating, they would say, so in this case, they would say, well, Sung said this. And so, the mentor described the informality as important because it allowed it to seem like you're having a conversation with a friend about, if you're talking about daily things. They didn't really want it to be as formal, but also the anonymity was important because you may not want a friend who's translating to know every single detail about what's going on with your life. And so the mentor and mentee could have this conversation through the system without maintaining some level of privacy. So we use the livelihood framework to sort of assess to understand the strategies and how they were changing with use of the system and the outcomes that it led to, so the livelihood outcomes that it led to. So I'll talk more about the strategies in the next few slides, but some of the outcomes that we've seen so far that the mentor-mentees were able to successfully accomplish was like enrolling a child in preschool, which they were having difficulty doing before, reinstating someone's medical care, avoiding tax fraud, and so on. Okay, so we saw a shift from missed appointments to more mediated requests, so the refugees felt empowered that they could now request help when needed, whereas before they sort of just went with the flow. We saw that the visits were now goal-oriented, so the mentors and mentees could sort of be a part of defining how they wanted help, what they should accomplish during visits. So I need my son to get in school and so on. As we said, scheduling was a use of it. And then one important thing was cultural clarification. So the interpreters themselves didn't want to just interpret. They wanted to highlight where there were cultural gaps in the communication. So in one instance, you had a woman who, she would ask her mentee, do you need to go to the grocery store? And the answer is always no. And she's like, I go to their house, I know they need to go to the grocery store, but they just keep saying no. And so I'm frustrated because I don't feel like I have use. So the interpreter, while I was interviewing, was like, you need to tell this lady that keeps asking to go to the grocery store that she needs to ask two times, and on the third time she should just insist, I'm coming to pick you up and take you to the store, because that's just the Burmese culture. Like, they'll always say no, so she'll never get anywhere until she just imposes. So that was useful. So we continue to look at and assess some of these uses of Rivrtran and make recommendations for similar systems. Thank you.
Great, thanks, Deana.
We have time for a couple of questions while Mason gets set up.
Should I ask a question just to have a question? Actually, I have a question. So you talk about the informality in an asynchronous manner. Did you look at all at what's been used in the deaf community for decades, which is an informal synchronous method, whereas if you do a phone call to a deaf person, a third-party operator does that for free. And now they do it they can do it with SMS, they can do it with video conferences, but it's a government-provided service.
Yeah, so I guess the challenge is one, the resources. So the interpreters in that, so I'm actually familiar with those systems. I went to RIT, so they had they use this a lot. I've used it to communicate with hard of hearing friends. So the challenge is with the resources. So we needed free labor in this case, because there's not enough funding to pay for interpreters and so on. And then we're limited, of course, by the capabilities of the refugees, what the devices that they had. So a lot of them on arrival just have that basic phone. So a system couldn't be any more complex than something that you could just dial a number and do. But that would be interesting. The other thing is that the agency did not want to create a tool that would become a long-term crutch. So it's actually, the system is sort of meant to be used on arrival and not follow you or after that, because it's important that they do acquire language speaking skills and all of these things.
But I would think that if there were strong enough findings for the asynchronous, you could make an argument to the agency that needed to run a synchronous equivalent at their cost, even for a period of time.
We should probably switch over to Mason just in the interest of time, because we got a tight schedule here. So let's thank Deana again. And next up, let's welcome Mason Bretan.
Okay. Hi everyone, my name's Mason. I'm a PhD student in music technology in the School of Music here at Georgia Tech. And I study something called robotic musicianship. And basically what that is developing robots that are capable of understanding and perceiving music, generating their own music, and interacting with people appropriately by sort of generating responses that seem meaningful towards the music that's being played. So creating all of these different interactions between humans and robots to create sort of new genres of music and this sort of expanding musical culture beyond just humans. And as you can see, there's lots of robotic musicians in the world. The one that I work with in particular is this middle one, Shimon, that plays marimba. But what I'll talk about today is some of my dissertation research in motion planning for these robots. And a lot of these papers which describe this sort of the generative algorithms about generating notes and improvising for these different robots, they're all there's no distinguishing factor between each one depending on the robot's embodiment. And embodiment is such a distinguishing characteristic between that and just a computer that I figured a robot should consider its physical constraints and its physical parameters when it's making musical decisions about how to play something or how to improvise and what musical decisions it should be making. So that's sort of the topic today is sort of creating a system that allows for improvisation, allows for a robot to play music based off of its own embodiment. What this is referred to is called path planning, and path planning is something very, very common to all robotic systems, and it's basically the spatial reasoning system for robots to make decisions about how to move and where to move, and break down these I guess these tasks into sort of discrete tasks that plan out how it moves in order to optimize some function based off of some physical constraints or whatever the goal is. So I guess if the goal has some constraints, it will sort of optimize for that. And there's two big challenges in motion planning in general, and that's the continuous state space, because there's continuous space where we are in these 3 dimensions, and then when you discretize that, it's a huge number of dimensions. So you are potentially looking at hundreds of thousands of these particular states that you have to search through. So you have to prune away a lot of this information. And so what I do with Shimon is Shimon has 4 arms, and basically I take Shimon's arm positions and I try to figure out a single state which represents each possible configuration where it can actually play a note. Because some of the area in between notes isn't really important for playing an instrument. I don't need it to be in a configuration where it can't reach a note or something. So each one of these states represents a physical configuration, which these red lines are in the state over here, and each one of those represents an arm position, each one of those red lines. And so the task then becomes trying to find an optimal path that goes between these states based off of its physical constraints. So you have these transition probabilities about how it moves, so you want to minimize for the distance and sort of this cost function that allows it to move, and then you also want to sort of prune away all of the impossible moves. So Shimon's arms can't cross over one another, so you don't want to consider these states which it can't make based off of its physical parameters. But even with discretizing it and minimizing these number of states, it's still a very, very large number of states, hundreds of thousands actually. And so what I've been doing to sort of optimize this function and actually make it usable is I use the Viterbi algorithm to move through this trellis of states. And if you're familiar with speech recognition tasks where they have millions of words, and sometimes in the dictionary they'll apply a beam search or a star. And in this case, I've been using Viterbi beam search, in which it chooses the best hypotheses and sort of ignores the rest so that it can optimize its function. And so instead of looking at all of the state space, it's probably looking only at 90 or 95% of the state space, and this allows it to move through the search path more quickly, and so then it becomes, instead of taking hours and hours or possibly days to create a path plan, it can compute it in hopefully minutes. And what I'm working on now is pruning it down even further, so hopefully it can do it in less than a second. So each one of these states represents a configuration, but then you can combine it with the musical score. So if you were to take a piece of music and represent each one of these states not just as a configuration but also as a note, then it will try to find the path in which it plays the note and it's an achievable configuration. So for example, if it were to take in a piece of music that sounds like this, so it would take in this information and try to create a path which optimizes its movement so that it can play all of these notes. So the first video that I'll show is the path planner that was used before I started working on this, that's been used with Shimon for the past 4 or 5 years, and you get a result that looks like this. And it can't really achieve what it's doing, what it needs to do, because it's sort of making these decisions sort of using an online method. And so instead of making every decision at the note time, I give it the entire score. It makes an optimized path for the entire score. And that looks like this. This sort of shows that it's working when it reads a sheet of music. So the next step that I want to do is not, instead of just having it play a pre-composed piece, I want it to be able to generate its own music and improvise. So a lot of these previous improvisation algorithms, what they do is they take a note and they might train a statistical model based off of Coltrane or Thelonious Monk or something like this, and create Markov chains. So you have these transition probabilities and these note probabilities, and based off of the previous note, it'll determine the next note. So instead of taking that approach, where you make a decision based off of every single contiguous note, it's creating note phrases. So it's taking chunks of notes, which are referred to as phrases in music. So it creates a phrase based off of these parameters that I input. So sometimes you might have a pitch contour that looks like this, or a tonal tension or density, and I've just developed all of these different models to represent these different musical features like note density, rhythmic complexity, harmony, and I tried to, I incorporated some rules or some probabilities that are inherent to jazz, and I gave it a way to sort of build these paths based off of each phrase that it tries to represent. So what I've been doing is I've been creating all of these different phrases, so I can draw these contours by hand, and then I've been creating a data set of that, and now I have this data set of all of these different contours, and I've been creating models so that it can generate these contours on its own using Markov analysis. So basically now it can generate it'll generate a contour, and then based off of those contours, it will generate an improvisation. And that altogether looks something like this, or sounds something like this. So if you have, so this is for, I guess, a robot that has sort of the physical constraints of what a saxophone player might have. Representing one set of contours and using the same exact set with a different set of physical constraints. And then finally, with another system which is very, very physically constrained. So you get different musical behaviors based off of the different physical constraints. So if I were to give my algorithm to my robot, and it would generate a response, and if you give it to another robot, it will generate, even if you give it the same musical parameters, it would generate a different musical behavior, a different musical response. And then, so these are simulations, and when I put it together with my robot, you get something like this. So what Shimon is doing in that case, it's listening to the chord changes that I'm playing on piano, and so it's figuring out the proper notes to play based off of my chord changes, and then also based off of these contours that it's generated, it creates optimal paths to play these musical phrases that it generates. So I showed generating a path for a precomposed melody, and now improvising, and so both generative aspects of music. The next thing I'll talk about is actually using the same method, but having it influence how the robot perceives or understands music. So the idea is to create an embodied musical cognition, which basically suggests that musical tasks or musical decisions are influenced by the person's body, even just by how they perceive the music. Because there's this theory that in embodied cognition is that you're simulating all of the, if you were to watch somebody play piano or something, you're sort of simulating what's going on with your own body, with your mind. And based off of these simulations, it influences how you perceive the music, what you think is interesting in the music, what you think is important. So using the same idea, Shimon or another robot can listen to the music and figure out what's important and what's sort of essential or interesting in the musical, the music that it's listening to. So for example, some notes, when you listen to a phrase, they're more important to others just perceptually because they act as cognitive anchor points, and so all of these other notes are sort of referencing that particular note. So even if there's like 100 notes in a phrase or something with a really, really high note density, there are some notes that stick out more than others and are more important. And so like in this the green notes highlighted here, there's been some musical studies which show how people sort of think or perceive what's important and what's not. So I can take all of those studies that have been done on humans and then apply my Viterbi algorithm to figure out how exactly Shimon would play this phrase, or how Shimon would sort of optimize its movements in order to play something like this. And it turns out that if it has a different set of physical constraints than a person, Shimon can't play all of these notes, so it's obviously going to pick the ones that it can play and which have important relevance in the music, so it picks a different set of notes. So these red dots are the ones where Shimon thinks are important, and a lot of them, or all of them, sort of overlap with what humans would think are important, but Shimon picks fewer than what a human would do because it's physically constrained in a different way. And so what happens is you get something like this. So in this case, the shimmy robots, that's what they're called, we're listening to the music and then trying to figure out exactly how to dance or create a choreography based off of the motif that I played. So it obviously, the motors aren't strong enough for it to move at that rate to hit every single note, so it has to pick a certain number of notes or what it thinks are important. So it picks, so you saw that it created these gestures based off of these important notes, and it creates these start and end times and these certain points in which it's trying to achieve a choreography which best represents this music. And so it's using the same sort of path planning or motion planning to perceive the music and understand and then create a choreography based off of its understanding. And that's it.
Could you tell us a little bit about how you did the gesture production, gesture design, where you go up?
Yeah, so for the shimmy robots, there's quite a bit of research that went into sort of the lower level stuff about how to move, like with using certain velocities or certain accelerations to make it look more natural. A lot of it was actually modeled off of people, so how people dance. It's not just sort of continuous velocities, but these different types of accelerations and decelerations. So a lot of that is embedded into how shimmy moves. And then it basically calculates a trajectory about what it thinks is an expressive movement. And based off of that trajectory and how it connects to the music, it creates the choreography. Yeah.
So if you were to have one of your earlier systems generate music that shimmy is able to dance better, would it come up with something that's kind of fundamentally alien?
Maybe. So if generate, maybe I don't understand the question. Generate.
Shimmy has restricted movement.
Yeah.
It can only move at certain times and certain beats in certain ways. And you're asking it to dance music, right? We don't know. I don't know anything about you, but it can't do it perfectly. We couldn't dance the same as you. So now you can feed the what shimmy's abilities are back into a music generator.
Right.
Generate music that shimmy can dance do better.
Oh yeah.
Sense of what that would sound like.
So actually, I think. So the first part where I talked about the generative algorithm, so I could apply the shimmy's physical constraints like as a coefficient to that generative system, and you could get a sense for what it might sound like if shimmy were to generate music. So in shimmy's case, it's a little bit, I don't know, it's a little bit strange because it doesn't play an acoustic instrument, so sometimes it's a little subjective about what it means for it to be connected to the music. So.
Great. Let's thank Mason again and welcome Alex.
Great, Mike. Hello? All right, that's working. Hi, so I'm Alex Zook. I'm a PhD candidate in the Human-Centered Computing program, and I'm here to talk about applying machine learning and artificial intelligence to improving game design. So the thing is, we're currently experiencing this golden age for game creation. Amateurs are able to make games now in all these sorts of events very rapidly. There's uses of games for purposes like education. We're even seeing games being applied to tasks like collecting data for machine learning or citizen science. But there's a problem. And that problem is making games is actually pretty hard. It takes a lot of time, a lot of money, programming, and quite frankly, one of the big ingredients here is expertise. You have to know how to make a game. And the reality is most of the people who are making these games or trying to use them are not expert game designers. It's just not a practice that most people have. Normally, these folks would just go and find the relevant textbooks or information to use in this field. But quite frankly, it's very, very scattered right now. We're dealing with an area where there's very conflicting opinions and no real understanding at a more grounded level as to how to go about doing game design. So this leads to a question. How can we improve game design and development? Are there ways we can support the process of making games and helping new people make games who weren't able to before? And the solution I'm going to talk about is an approach I'm calling a science of game design. It's an effort to formalize this notion of game design and use computers to help augment that process. So when I'm talking about a science of game design, what I'm specifically referencing is this idea of building formal models that predict how elements of a game design work to influence factors that are outputs of that design. So if you have players, it's their entertainment and enjoyment and their behavior. If you have a citizen science project, it's the quality of the data. Ideally, what this will let us do is begin to formally study and automate and even augment some of the processes in game design. So everything from asset creation, where you're creating the basic art in the game, all the way down to playtesting, where you have people play the game and have someone observe it and understand what's going on. And my hope, by pursuing this sort of direction, is to enable us to better formalize, augment, and eventually build generalizable and reusable knowledge about game design. And when we're talking about that, it's everything from the content of the game, like the way the world is arranged, through the actual behaviors we can expect players to have when we design a game in certain ways. The methodology I'm advocating here is one based in artificial intelligence and machine learning, where these systems will formalize testable knowledge about how game designs function and use this formal hypothesis-driven approach to then use computers to facilitate and automate the process of acquiring game design knowledge and bringing that to bear in game design practices. So there's naturally a question, why would we do this? Why should we try and turn game design into a science? And one of the fundamental reasons here is scientific study. Just as much as we want to study the mind, not the study of the mind or study cinema, we also want to study game design as a fundamental area of understanding. It also can lead to the capacity for new intelligent tools that help augment the way people can go about their everyday practices, or even enable new kinds of practices, new ways of going about designing games. And there's also fundamental questions about computational creativity. Can computers be game designers autonomously, on their own? Can they make games for us? And what would that mean, and how far can we go? So over this talk, I want to briefly touch on a few areas that I've been working on and trying to build towards this science of game design. And this is really around the idea of enabling computers to formulate hypotheses about how game designs work, generate games to test these hypotheses, and then analyze the outcomes of these game tests to understand how they contribute to our knowledge of game design. In terms of the computer itself, this means it's gaining increasingly powerful capabilities to make games, structure them, and then understand how they work. So where do we start? Game design is very messy. There's a huge number of factors involved. What's the best place to enter into this problem? We'll start by looking at parameters, these very low-level just tuning constraints into game design, and try and understand how do these work, what is a game design hypothesis, and how can computers formulate these and then use these to build more knowledge. So how can a computer go about evaluating a game design? And the answer I would propose is run playtesting, same way people do. So playtesting is this process where you have a bunch of people go and play your game, observe them, collect various data about their play, and use this to inform further iterations on your design. Practically speaking, it's a very simple loop of taking a game, running a playtest, analyzing the results, picking some changes, and repeating. So can we formalize this process? Specifically in a way that is amenable to artificially intelligent systems? The answer, of course, is yes, or I wouldn't be talking right now. And the approach is to use machine learning as a way to predict the outcomes of a specific design, and then a subset of techniques known as active learning that will go about picking the next design to test to learn the most about the space of possible designs you can do. Just as a very abridged thing, there is in fact boxes and arrows involved, so we are doing computer science. And the approach here is we will take playtest results, use machine learning to predict outcomes of those playtests in terms of player behavior, and then use a set of techniques known as active learning to consider possible untested designs, and then use these to pick one of these untested designs, run a test on it, and collect new results. The goal here is to minimize the number of times we have to go through this process so that humans don't have to run an infinite number of playtests with people, but can actually just get a small number of players. We ran 2 case studies in this based on a game that's a simple shoot-'em-up game. So the case studies varied things like the parameters for how the enemies behaved in the game, as well as the controls to look at how well can AI optimize for things like player preferences for controls. The results of these studies were very promising. So what this chart is showing you is on the y-axis is how much does this technique improve over a naive baseline playtesting approach. And this is run on real people online. And on the x-axis is the number of playtests run. So So what we're seeing here is that overall, with very few playtests, we're getting very large benefits. As we eventually reach the point of having infinite data, it really doesn't matter how smart you are because you just know the entire world. So this is very sort of strong results in showing that this technique can in fact help, and makes these first steps towards this notion of enabling computers to formalize hypotheses about the right designs to test, run those tests, and automatically search through this parameter space. Further, this is opening the potential for playtesting to be more efficient in human practices and augment those approaches. Of course, there's a challenge here, which is I've so far just talked about tuning parameters, and that's wonderful, but games involve a lot more than just the parameters for game elements. And in fact, they have an entire context, world, and environment, and other things going on in the game. So how can we enable a computer to assemble this full environment? Not just tweak some parameters in a given design, but in fact build the entire design from the ground up, assembling semantically different content, and do so in a way that acknowledges differences in players so that it's better able to create the games that it needs for a particular audience. When I'm talking about game content here, I'm talking about things like the plot of the game, the world and how it connects and guides the player through it, as well as the actual entities within the game. Everything from the individual NPCs that are occupying the world, through the items that are usable in the game, or various decorations in the environment that really create the entire experience of playing that game. So the question is, could a computer assemble and personalize one of these game environments to a player? The answer again, of course, is yes, or I wouldn't be talking. We have built this system called GameForge that combines information about a game story with particular information from a player on their preferences and a designer on their aesthetics for how the world should work. And with further information about how to design things like the environment and how to script the behaviors of non-player characters, this system is able to produce full game worlds. What this ends up looking like is taking a story, some player preferences, a world, and generating a layout of the world that eventually gets grounded out to embed that story within a game world, and then decorate the environment, control the NPCs within the environment, lay out the items, and create the full game test bed that you can then run additional design tests within. Some of the examples of the worlds generated here can vary things like how much the world branches, how linear it is, and in that way account for some of player differences in terms of their preferences for how to go about exploring the world and interacting with different kinds of worlds. And we've done some follow-up work to actually study how well does this work, where are the strengths and weaknesses. So what this contributes is our ability now to construct full game worlds, full environments that are actually integrating multiple types of content, and in a way that actually creates a full test bed experience for a player. This enables us to combine both designer control in terms of the content they want in the game with automation through the system. And this is one of the few systems that currently exist that can actually do the entire process of generating a game. But again, there's a challenge here, which is, so far I've told you we feed in all this information to the game system and it's able to create this world. What we really want is something closer to sort of a built up from Lego blocks world. We want a system that can assemble all the small parts of content to create a full game experience and shape the player behavior rather than rely on pre-baked knowledge from a designer. And it's only by taking this sort of ground-up approach that we hope that we stand a chance at trying to do things like build games that bridge multiple genres or spread across many areas rather than being tethered to the particular choices a designer has made in their high-level goals. So our goal in this phase is to understand what's a representation for games, the way games function, that is domain agnostic and can be used to actually generate not only the content in the game, but also the actions, the types of mechanics within that game, ideally from scratch, and do so in a way that can actually guarantee that designers can shape the way players behave in those games. So when you run various things like design tests, you can try and create designs that create the behavior you desire. So the goal here is to start from something like a very simple description in a game of, here's the state of this thing, it's called a Mario, and it just is there. And get to the point that it actually creates actions, what I'm going to refer to as mechanic generation. So the creation of jumping when all you knew was that Mario was a thing in the world that had a position. But there is a challenge here, and that's the way Mario works right now is Mario can jump and go hit the block. But why not something like this? What tells the system, what lets it know that this is a bad jump and the one on the left is actually a good jump? And the solution here then is to enable the system to actually test the outputs it's producing. So up until now we've talked primarily about systems that produce something and evaluate what comes out, rather than trying to ensure that they have certain functionality or properties. So at a high level, it's a relatively straightforward approach. We have a system that generates a set of mechanics and then tests that they do in fact work in the game. In practice, it involves a couple of underlying systems that solve for a set of constraints about how the mechanics should function, and then validates them within the game world to show that they can in fact produce the desired behaviors. In practice, what this ends up looking like in a simplified 2D platformer domain, similar to Mario where you run and jump, is you have a player, an enemy that the player is killed if they overlap, and a goal that the player is trying to reach. And the system is able to then generate a set of mechanics, here are solid arrows for movement, that it then validates can in fact reach the goal state in the game. And it can do this in many different ways to produce multiple solutions and test variants that would all solve this problem of beating this level. So in this level, you can get multiple solutions. One type of inventive solution the system will create is to actually chuck the enemy behind itself instead of just running and jumping into the goal. Alternatively, the system also was creative in a sense, as it decided it was much easier to just ride on top of the enemy than to bother jumping to the goal itself. So there are a number of applications and extensions of this approach because of this sort of ground-up technique it's taking. We can do things like combine pre-existing game domains to generate new kinds of games that haven't previously been built. We can adapt mechanics and serve designers by using this system to validate that changes to their design still fulfill some of the functionality they want. We can also do things like progressively introduce different types of content in the games to fully use the systems that are being built, and even go so far as to generate the controls for a game. So the ultimate contribution of this work is this notion of a representation for how games work, and a process to use that representation to generate the actions in a game and a variety of other things that then fall out from that representation. And the approach is this fairly straightforward technique of working from very low-level primitives to construct games. So all of this is bringing us towards this science of game design, but this naturally leads to the question, so what? Why do we care? And there are a number of useful applications and extensions that I've been pursuing in my work and over the course of my work. Currently, a lot of this work is targeted towards the use of games for things like personal training and data collection or assessment. So in collaboration with the ACT, we're working on automatically generating games that can assess various parts of various aspects of people, everything from their personality to their disposition towards their skills. You can also use the same kind of approach to try to generate games that are useful for collecting data. So collect common sense knowledge about where can I purchase various items in the world, what kinds of games are effective for that, and how should they be designed for different player audiences. And ultimately, I think this is going to move us toward having a set of systems that can really collaborate and work with people towards building the kinds of games they want. We'll get past the point that games are currently treated as these sorts of incredible efforts that require massive expertise to be something that anyone can engage in. So I'd like to just thank everyone who's helped me, my advisor, my lab, and funders, and thanks. I'm open for questions.
So I would assume that you have pretty different kind of computational models for different genre of games, first-person shooters versus platformers and stuff. Are there some of these that you think are going to be more amenable to this approach versus less amenable? Or?
Yes, so definitely. So the representation I talked about with the generation is targeted towards these sorts of discrete and turn-based domains. So this covers many genres. So you can do a platformer in that, you can do many puzzle games in that, but a first-person shooter becomes more difficult just due to the perspective and everything else. And I think a lot of the work within this will always have to balance between the ability to be very general and flexible and the ability to be computationally realizable and useful. And so the goal is to enable these systems to capture useful chunks of the design space rather than try and create the most generic system possible, which is going to be, a halting problem. So.
Good questions. Great. This is a fantastic set of talks. Let's thank our speakers again.